So we are going to pick up where we left off on Wednesday. That is talking about the electric forces, and the topic of the day is electric fields. So we're going to learn about field theory. Yay! And we start with a review question, which hopefully is going to now work. I've got these theories about how to make this program work right. So a particle with a positive charge of plus q is the distance r from particle with negative charge 2q. So there's our physical arrangement. The Coulomb force that the positive charge exerts on the negative force is plus F. So the positive on the negative means it's the force going like this, where F is the magnitude, the plus sign indicates the direction of the force. What's the magnitude and direction of the Coulomb force that the negative charge exerts on the positive charge? And Christian, I got your email. I haven't had time to actually look at it. I think it's okay, but I want to check before I respond. Do you have to have it today? By Tuesday? Yeah, I think it's Tuesday. Anyway, I will get to it. Okay, we're less than half in at this point. But at least you brought it this time. Yeah. Okay, so still missing Brittany, Angelina, and Alex, and of course. Still logging in, Brittany.
What is the session?
The session is web PHYS. Okay, Brittany. Didn't mean to throw my pen. So excited. Just to answer a question while she's typing in, Erica asked about this grade scope thing that you apparently got emails from. That's where I'm going to be grading like the labs and stuff. And so, or at least I think I'm going to be grading there. It's kind of experimental. I didn't think you guys would even see it. You know, it's just the grading, but that's what it is.
So do we still need to like sign in on it?
I don't think so, at least not at this point. If you do, I'll let you know. Still working on it, Angelina? Okay, I'm going to go on because got to get through class. We have 35055. We had quite the variety of answers. Yeah, that wasn't what I expected. So turn to the person next to you and discuss physics about how this might work.
Yes. Yeah. It says this up there. Because
I hope I call on you. Excel's perfect. There's another answer you could have given from first semester as well. From like week 2. I mean, another explanation. Okay, let's do it again and see how we do in round 2. So it's open for answering. So everybody answer a second time. Did you get logged in, Angelina, or still no? Rebecca. Okay. I'll work with Angelina separately. She doesn't have a semester's worth of doing this. So, second time around, our answers are a little bit different. Okay, so James, give us, well, first of all, you notice that there was a big change from positives to negatives. Why, that's a correct change. Why would it be a negative?
Because it's just opposite, and there's a negative Q charge, so therefore, since there's a negative Q versus a positive, negative force, probably in the negative direction.
Okay, that was a little more than I was looking for. Because it's attractive on the other charge, it's got to be the opposite direction. Now, is it minus F or minus 2F?
Just minus F.
Okay, just minus F. And what was your reason for saying it's just minus F?
Because one positive and one negative, or not, I said it just that.
Or, yeah, just minus, yeah.
I said that because they would cancel each other out.
To give you,
You want to only negative or minus F.
okay, there. I'm not sure I followed exactly your reasoning. Doesn't mean you're wrong, so don't take it the wrong way. There are 2 ways to answer this. The one that I heard Gila explaining was perfect. We have Coulombs Law, which says that the force magnitude is K, magnitude of charge 1, magnitude of charge 2, over the separation squared. And so that force magnitude, doesn't matter if you're on charge 1 or charge 2, you're still going to have charge 1 and charge 2 and the separation between them the same. So the magnitude has to be the same. Only the direction can change. Different way of answering it is going all the way back to the second week of first semester. We learned Newton's second law, or his first law, either one of the word, that says net force is mass times acceleration, or if it's an equilibrium, net force is 0. Or his third law, which is the one I really meant to go with here, that for every action there's an equal and opposite reaction. So if charge 1 is putting a force on charge 2 has to be putting an equal force in the opposite direction on charge 1. So even if we've never heard of Coulombs Law, we could have used that to answer to say that the correct answer is the one that James chose, minus F. Okay, now to the electric field. And when I talk about the electric field, I always preface it by putting something we're comfortable with. Fields, I think, can be confusing in physics. But we've already talked about a force field for a long time. The force field we've been talking about is the gravitational force field. What is the true equation, as far as you know, for the force of gravity between 2 objects? The force of gravity is a constant G times gravitational charge 1, M1, times gravitational charge 2, M2, all divided by the separation between those two objects, r squared. And we said if we're on the surface of the Earth, we defined G to be the force of gravity divided by mass 2, which according to that universal law of gravitation is capital G M1 over r squared. And we said as long as we're on the surface of the Earth, that G is going to be roughly the same because the mass 1 is the mass of the Earth and the r is the radius of the Earth. And so we've been talking about this gravitational field. And we've talked about the word gravitational field. That's what a force field is. A gravitational field is a force field. You watch sci-fi movies and they talk about a force field, and it seems like some mystical thing. You know, gravitational force field, it's a field is something to help us calculate the force. And so with gravity, we took that gravitational force field G, and of course it's actually a vector field, so we had G vector, which allowed us to then find the force vector. The force due to gravity was equal to the gravitational charge multiplied by the gravitational field. And so we've been doing this process every time we do force of gravity is mg. We've been using a gravitational force field. Now we're going to take that same exact thing and apply the same idea to electricity. So we're going to make an electric field. So we'll call it E for electric. And that electric field is defined as the electric force over, and when we did the gravitational field, the gravitational force field was the force of gravity divided by, what was it divided by? The gravitational field was equal to the gravitational force divided by, you can say it, not sophisticated, G equals Fg over M, over the mass, or as I now have been calling it to try to familiarize ourselves with terms, the gravitational charge. So for the electric force field, it's going to be the electric force divided by, instead of the gravitational charge, it'll be the electric charge, which we conveniently enough just call charge. And so the electric force field is the electric force divided by, and I'll put charge 2 just to be completely analogous. And so we can use that at any point to find the electric force is whatever the charge is times the electric field. So the whole point of electric fields is to be able to do this, to be able to calculate the force on any charge based on the force field, the electric field. So we have a globe here, a globe here with a negative charge on it. If I were to put a positive charge outside the globe, would the positive charge be attracted or repelled? Attracted, because opposites attract. And so there's going to be a force on a positive charge that's inward toward this globe, no matter where you go. And so I'm going to calculate the electric field is equal to the force I would get So I have Coulombs Law on top. K, Q1 is capital Q. Q2 is the lowercase q over r squared, and then divide all of that by q. But notice these q's are going to cancel. And so I'm left with the electric field. Now, what's missing from my equation? On the left side, it is a vector. Needs to have the direction there. The minus r hat is because it's inward toward the charge instead of r hat away from the charge. So that's how I get the electric field for my charged globe. As long as the globe is spherically symmetric, I can treat it like a point charge. That's why I use Coulombs Law that's the force between point charges. So the electric field is here to help us calculate force. Now I can take that electric field, and the electric field is KQ over R in the minus R hat direction everywhere. It's a vector field. It has direction. What's the difference in this vector field? Oh, and I forgot to put a square. Somebody should call me on these mistakes. What's the difference in this force field and the gravitational field? Yeah, okay, the strength. That is a definite difference. It's not the one I'm looking for, but it's certainly a right answer. What I'm looking for is fundamentally nothing. The only thing that's really going to be different is the size of this globe is small compared to how far away we are. We can easily move and change the R by a significant amount. And so this force field is going to be much more fluctuating than we're used to thinking about with the gravitational force field. But otherwise, it's just the same. The gravitational force field points in toward the Earth. And it's spherically symmetric. So it's just like our gravitational force field. And we use this gravitational force field to calculate the force of gravity anywhere. And so I can say, okay, Richard has a mass of, let's say, 120 kilograms. I don't know. I haven't calculated recently. So what's the force of gravity on him? Well, it's going to be down wherever he is. Down means toward the center of the Earth. And it's going to have a magnitude of mg. Well, Angelina's mass is less than half of Richard's mass. So what's the force on her? I take that same force field and multiply it by her mass. And I get a smaller force. And I get the vector. And so if Angelina is in Taiwan instead of in the United States, the direction is going to be still toward the center of the Earth, but it's going to be a different direction because of the different location. So now with the electric field, we do exactly the same thing. If I have some charge, here's a charge of 120 microcoulombs, I just say, okay, 120 microcoulombs times the electric field here gives me the force, magnitude, and direction. But there is an important difference that I didn't talk about. Gravitational charge only comes in one type, positive charge. Electric charge comes in two types, positive and negative. If I have a positive charge, it's going to be exactly the same as it was with gravity. But with a negative charge, what's different? The direction is reversed because of the negative charge. So if I have a negative charge out there at point P, the force of the negative charge is going to be outward instead of inward. So electric force can be attractive or repulsive. We have that difference. So what's the point of an electric field? What's the whole reason we have it? Go out loud, Lauren. She doesn't even say no out loud. The whole point for having the electric field is to allow us to easily calculate the force on any random point charge that I place. Now you'll hear us, and you'll read about more than you'll hear us, read about about test charges. And we'll say, a positive test charge. Well, what does that mean? Basically, if you'd had a positive test charge, the force on that positive test charge would be parallel to the electric field. If you had a negative test charge, it'd be the opposite direction. It's just a simple way to think about it. It's not something to get disturbed about. I did notice that. Then it is easy to calculate the electric force, Fe, on any point charge placed there. That's the point of electric fields. The point is to make it easy to find force. Now, as we go on with things, we'll start treating fields like there's something really there, like they're physical elements. They're not really. They are just telling us, if I put an object here, it's going to have a force because of that. But there's not something actually there. All the way up until we talk about electromagnetic waves. Then we have energy traveling. Gets a little more confusing. Okay, clicker question. A point charge has a net charge of minus 10 nanocoulombs. What direction do the electric field lines point? See, I figured it out. Okay. There you have it. Brandon. I've just randomly grabbed from the middle of the pile. It's completely random. You guys were sitting next to each other, just in case you're worried.
I put E from doing the homework and stuff and reading the thing when it's negative.
Have we had homework that dealt with electric fields?
On the reading.
Oh, okay. Okay. I was like, man, I thought I was more careful. Okay. That's right. Negative, it goes in. So electric field always goes into negative charge. What about positive charge then? What happens if I have a positive charge? Okay, positive charge, then the electric field goes out. So a very simple problem. It's a simple problem because, well, we want to start you with easy, not start you with hard. So we have, again, a small pith ball, spherical mass, has the mass given to you. Since it has the mass given to you, there's a good sign that we're not going to ignore the force of gravity. It's hanging from vertically from insulating thread that's 12 centimeters long. By charging some nearby flat metal object, we don't see it, we create an electric field that has this magnitude. And it swings out as shown. So you can see the electric field direction is shown with the green arrow. And then it asks, what is the angle that the thread makes? How would I approach this? How would I find that angle? Okay, I am going to use trigonometry. What physics principle? Oh, I'm sorry. I never did answer your question, Alex. What was your question? I totally forgot. I told him I was going to get back to him and I skipped it. What physics principle would I use here to find the angle? Because if it's on a test, you got to come up with that. There's a couple different things you can say. One of them starts with EQ. Equilibrium. It's an equilibrium, which means that sum of the forces is equal to 0. What I was teaching about in physical science this morning. So if I'm going to do sum of the force equal to 0, what do I have to do on my figure? Because it says, as a result, the sphere is displaced to that position. So it doesn't say it's swinging, it says it's displaced to that position. So equilibrium means it's not accelerating. If it's at that position, it's not accelerating.
Free body.
Free body diagram. So force is acting on this object. What are the forces? Gravity points what direction? So we have the force of gravity equals mg. Next, tension. What direction is that going to act? Along the string, away from the object. And there's one final force. What's that? I'm just going to assume you said electric. Yeah. And so that's going to be pointing parallel to the electric field because it's because it swung out that way, I knew it had to be to the right. So I have my forces. I have my equation that says if I add them all up, it has to be 0. And then I'm going to do exactly what Edward said. I'm just going to add these graphically. So I will have force tension, force electric, force of gravity equals mg equals QE. And there's theta, the angle. I don't know what theta is, but I know this side has, I'll just change colors. This side has a length of 12.0 centimeters, and this side has a length of 6.00 centimeters. So that means sine of my angle is equal to 6.00 centimeters over 12.0 centimeters, or 1/2. And from that, I can find the angle is 30 degrees. And then what's my relationship between electric field and gravitational field? Or excuse me, electric force and gravitational force? Using trigonometry, as Edward said. Okay, well, one's the opposite side and one's the adjacent side. What function relates opposite and adjacent sides? Tangent. So we'll have tangent of 30 degrees is equal to QE over mg. And thus, I can solving for Q, right? Yeah. Q is equal to mg tangent of 30 degrees over E. So one thing you note is we certainly can't lose track of the physics we learned first semester. We're still using it. It's just a new force that we're using it on. So I'm not putting in the numbers. Now that even then, what's the easiest way to find the tension? Yeah, you could use sine or cosine at this point. I would go ahead and use cosine because I was given m. And so I would say cosine of 30 degrees equals mg over force tension. So force tension is equal to mg over cosine 30 degrees. Two mg over root 3. I guess I could have finished this out too. So, right, that's just putting in what tangent of 30 degree is, what cosine of 30 degree is. And what's the final one? What is the charge on the sphere? Oh, wait. It had Q here, and so I found the charge first. That Q is because it was supposed to be changed to a symbol font and show theta. So I already found theta. That was the first thing I found because, well, I had to use it. So Not overly difficult, but you have to think back to the ideas. So the whole thing about physics is putting these ideas together. Doing the actual work once you have the ideas is usually, a letdown because it's not very difficult. I already worked this out for point charge, the electric field strength. Wow, I really should have paid more attention to the spacings. I changed the ratio of the size of the slides, and aspect ratio caused me problems. Here is a standalone statement that's so important I gave it a slide to itself. The electric field at any point is the vector sum of the electric fields at that point caused by all of the charges. So if I have something like 3 charges, and I say, what's the electric field here? I just say, well, charge number 1 makes an electric field like this. Charge number 2 makes an electric field like this. Charge number 3 makes an electric field like this. I add them as vectors to get the total electric field. So it's just adding vectors. Once you know the equation to find the electric field for a point charge, you find it, you add them up. So this is a simple case. Why is it simple? Well, with 2 charges, it's always a straight line relationship. And if we stay on that axis, 2-point charge, it's no vector problems. 2-point charges are located as shown. What is the magnitude and direction of the electric field at point P due to the 2 charges? So really quickly, I just said, what was my method? Add the electric fields as vectors. So I just calculate each one separately. So electric field 1, notice the x direction is defined, so I can use a vector and don't have to do anything special. If that's a positive charge, what direction is the electric field going to point for a positive charge? Away. So away is going to be in the positive x direction. So I'm just going to put here in front x hat in the positive x direction, and then it's k times the charge over distance 1 and 0.4 plus 0.8 is 1.2. And notice I forgot to write squared, but I got it in the end. So there's electric field 1. And then for electric field 2, I'll actually color coordinate 2. That's a negative charge. What direction should the electric field point for a negative charge? Into it. So there's electric field 2. My direction first minus x hat. I forgot to put the direction up here in the second writing. K Q2 over R2 squared equals K times Q2 is 0. Now, the astute might notice that when I wrote this down, Q2 is a negative number, and I didn't put the negative number in. Why did I not put in the negative sign? It's affecting the direction. I'm doing the direction separately. If I had been real careful, I would have put an absolute value sign here because I'm only finding the magnitude. So there I have my 2 calculations for the electric field. One's in the positive direction, one's in the negative direction. And so I put these together, and my electric field total is equal to electric field 1 plus electric field 2. And since I did not calculate any numbers, I'm going to stop there. You can all see how it works out. There will be a place, because these are in opposite directions, there will be a place out here where the electric field is 0. What would happen if I put a positive charge at the location where the electric field is 0? What? Nothing. Nothing would happen because the net force on it, if the electric field is 0, then the force due to electric charge is going to be 0, and so it would be stable. Now, if I move it away from there, depending on which direction I push it, it would move. If I bring it from that place where the electric field is 0, if I bring it closer to the charges, it will have a net electric field that is pointing to the left, and it will go left. If I take it farther away, then it will point. Yeah, actually, I didn't check which charge is bigger. Yeah. If I go far enough away, it'll go right. And so it will behave differently depending on where you put it. All right. Another practical, lots of problems today. 3-point charges are placed in the corners of a rectangle as shown in the figure. What's the electric field due to these 3 charges at the 4th corner? How is this different from what you were doing in the homework that's due tonight? Instead of force, it's calculating electric field. What's the fundamental difference? You don't have a charge here. You're finding what the electric field is, and then you could have said, and if I had a 4th charge there, then the force on it would be the electric field times the charge. Fundamentally, it's the same work. It's just now we're doing it with the electric fields. So this is just like what you're doing in the homework that's due tonight. So you just take this charge here is going to make an electric field that goes that direction. This one here is that direction. That one's that direction. You calculate those 3 magnitudes. You use your geometry to calculate the angles. You add the x components separately from the y components. You combine them to find the magnitude and the angle. All things that you learned first semester. But there are some rules about electric fields that you didn't learn first semester. It's often going to be difficult to visualize electric fields because you have all these arrows pointing different directions. So what we do is we draw electric field lines that illustrate how the electric field varies in a region. That's what my picture at the top of the lecture was. It was electric field lines. There were ones really close below. Uh-oh, what happened? Here we go. This is showing electric field lines. Now I'm going to come back. I have all the words down below, and then I have pictures. But I'm just going to talk about the electric field lines with this initial figure. First thing you notice is that the electric field lines are going out of the positive and into the negative. We've already talked about, and we said it's a rule. It is a strong, fast rule. Electric field lines always go out of positive charge, always go into negative charge. And the number of field lines that go out or come in is proportional to the charge. So if you look at this, even if we didn't have the numbers for the charges, you can see that coming out of the one on your left, there's 1, 2, 3, 4, 5, 10 lines. And the one on the right has only 6 lines. Did I have them right? 1, 2. No, I did not add them right. There are, it turns out, not 10, but is it 12? Yeah, there's 12 lines on the left one and 8 lines on the right one. I missed the horizontals, and I just didn't count. Yeah. Anyway, so we have 12 and 8. And that tells us that the ratio of charges is 12 to 8. And so we look at the charges that are given, 3 to 2. Yep, that's 12 to 8. Multiply both by 4. And so you can determine the ratio of the charges by just looking at the lines. You can tell which one's positive and negative by looking which one it goes into, which one it goes out of. And a third thing is you can tell the relative strengths from the lines. Where's the electric field strongest? Close to a charge or far from the charge? Close to a charge. If you look at that picture, close to the charge, the separation in lines is small. When you get farther, the separation is bigger. So the strength of the electric field is inversely proportional to the line spacing, the separation between lines. When the lines are close together, it's a stronger field. When they're farther apart, it's a weaker field. So we can determine all of that, plus, of course, if I randomly put a charge here at point P, the force in that charge is just going to be the magnitude of that charge times the electric field vector. So there's a huge amount of information held in those electric field lines. The direction of the electric field is always in the direction tangent to the line. Tangent means the direction the line is at that point. And we talked about the strength here. So let's see if you understood. How do electric fields add? Okay, 19 out of 19 said is vectors. Thank you. Sometimes I wonder, but we were all paying attention on that one. We've already talked about the direction and the number of lines be proportional to charge, so I don't really need to spend much time on that. When we have two charges, it's more complicated than one charge. One charge was very simple. In isolation, the lines are just radial, going in or coming out. But with two charges, you have to add them together. And so are you ever going to add it exactly right? No, you're never going to be exactly right. It's pretty hard, right? We use computers to calculate exactly what the strength and directions are. But you can see that if you have a stronger charge, then you can have an asymmetry where that stronger one maintains looking like it would in isolation for a bigger distance than the weaker one. So you see the stronger one, the place where they seem to go parallel is farther from the stronger, closer to the weaker. And so when you draw them, you just try to do your best. A really important rule for a very simple reason. Electric field lines can never cross. And the simple reason is the net force is the direction of the electric field. If two electric field lines cross, what direction is the electric field at that point? Yeah, two different directions. We can't have two different net forces. It's a net. The electric field is the net from putting everything around. And so the net, you can't have two different directions at one location. So it's absolutely impossible. Okay, another clicker question. Which statement is untrue about electric field lines? It's a little harder because it's which one is untrue. If this one is randomly Michaela, you'll never believe me. Good, it's not. Wait to hear that. And Erica. Okay, you just answered. It's just Brittany now. Okay. So we had 8074. Okay, good. Initially, somebody answered, one of the first answers in was electric field lines cannot cross. And I was like, but we just said that. Okay, so everybody realizes that statement is true. They cannot cross. But we have no majority. Got a plurality on electric field lines indicate the direction of force on negative charge. Nice, I would like you to explain to people what the correct answer is and why.
Because the separation between electric field is proportional to Q.
It's actually A. Last year I had the slide with the wrong wording in there to match what you said, which was incorrect. It's actually A. The separation is inverse to the charge, or to the strength, I mean. So when the lines are close, when the separation is small, you have a big strength. When the separation is large, you have a small strength. So that's an inverse relationship. So the correct answer was A, the electric field lines indicate the direction of force on negative charge. They indicate the direction of the force on a positive charge. So the problem there was the sign was wrong. All right. I have some dipole stuff here that I was going to take out, and then I thought, well, I'd leave it in just in case we have time. We don't. I want to talk about lightning rods in our last few minutes and why they work. So we start with fundamental thing about a conductor. In a conductor, well, what is the fundamental thing about a conductor? What's the fundamental description that makes something a conductor? The charge can move. So in a conductor, excess charge can move. So if you put excess charge on a conductor, or if you take away charge, then you have excess positive charge. We still think of it as excess charge. That charge can move around. If you have an electric field and the charge can move, what's it going to do? It's going to move. And so if you have a conductor, anywhere inside of the conductor, if there's an electric field, the charge is going to move because of that electric field. But when the charge moves, it changes the electric field. And so the charge will continue to move until you reach the situation where the charge that's in the center doesn't have a net force on it. What does that tell you about the electric field inside of a conductor? If there's charge there, but there's no net force, the electric field must be zero. So the electric field inside of a conductor is always zero. As a result of the electric field inside the conductor always being zero, it turns out that all of your excess charge always resides on the surface of the conductor. So you just have a uniform, neutral charge all through the conductor until you get to the surface. And then you have your charge on the surface. Now, the electric field lines, when you get to the surface, let us suppose that you had the electric field line is like this on the surface. I have an electron on that surface. The electron is going to have a force due to that electric field. Now that says F, so it's going to be opposite. The electron is going to have a force due to that electric field on the surface. And that force will have a component that's parallel to the surface if the electric field line is not perpendicular to the surface. What do we call the real world? Not perpendicular, but normal. If the electric field line is not normal to the surface, there's going to be a force on the charge that's parallel to the surface. There's going to be a component parallel to the surface. And then the charge is going to move along the surface. And so the charge will once again redistribute itself until the electric field lines on the surface are always normal to the surface. So no matter what the shape of your object, the electric field lines have to be normal to the surface. As a result of that rule, it turns out that the charge is much stronger at sharp points than it is at blunt points. So here it's blunt, on the other side sharp. The charge density is much bigger when you have a sharp point. Having that bigger charge density means you make a stronger electric field. So the electric field is much stronger at sharp points. Well, what difference does that make? If you have a strong enough electric field, you can rip charge away from a surface or pull charge from the air into the surface, depending if it's a positive or negative charge. That is the surface. So people early on, Benjamin Franklin, I believe, after he ascertained that lightning was electric, developed lightning rods. Lightning rods are little rods that have a sharp point. The purpose of that sharp point is twofold. The primary reason, it makes a really strong electric field so that you will have charge that bleeds off. Now, if it's positively charged, it'll be electrons coming in, but it will neutralize because you have really high electric fields. Why do you like that? Because if you neutralize the charge, you're not going to be attracting lightning. And so you have conductive things that go to these little pointy things that just bleed off the charge. If you look at our church, you'll see that the church has on the eaves, every foot or so, a little point sticking up. And that's what it is. It's a little lightning rod to bleed off charge to make the church less likely to get struck by lightning. If the church is going to be struck by lightning, because you have the much higher electric fields here, it's going to be there rather than some random place. So a secondary purpose here is if lightning's going to strike it, to keep it from striking somewhere else, hit something where you've got a wire going to ground. Okay, I went too long. I apologize. We all have to run.